Welcome to the Around the World Symposium on Technology and Culture, organized by the Cute Institute for Advanced Studies at the University of Alberta. This is part of an international event run at 13 different institutes at the same day. We repeat it every year. This is the second year that the University of Alberta is participating. Last year, the event was on privacy. It was hosted also by the Information Systems Department. And this is part of the weekly research seminar of the Information Systems Group at the University of Haifa. We are happy to have here today with us 4 leading experts on big data from industry and academia, Israel's leading experts on the topic. We'll have a panel about 1 hour and then questions and answers from the audience. Okay, and I think that we're ready to begin. My name is Araki, and I'll give the mic to each one of the speakers to briefly present himself.
Hello everyone, I'm Bickson. I'm co-founder of Dato. We are a US-based company which provides open source tools for big data analytics.
My name is Assaf Araki. I'm a big data architect at Intel, and I'm part of a division within Intel that build a big data solution mainly based on machine learning.
Hello, my name is Kemelmakher. I'm from SAP. I'm responsible for SAP Innovation Center here in Israel, which is a part of Innovation Center network established in SAP. It's an SAP version of a research organization which is busy with applied research topics, new markets, advanced engineering, etc.
Hi everyone, I'm Bekkerman. I'm from the University of Haifa, assistant professor of data science, dealing with big data issues like on a daily basis.
So the first question for the panelists is, what in your mind is big data? Is just the amount of data? We're dealing with a particular data structure, the velocity of the data, and just take turns who wants to.
I guess the formal definition of big data is the data that cannot be stored and processed efficiently in a relational database like Oracle. And it's all about the size, the volume. We all know about the 3 V's, right? I guess I shouldn't declaim it again, but to me, the volume is the most important part of big data.
I would like to offer another point of view. We know the volume, the velocity, and the variety, but maybe as an hardware company, we are looking whether the processing that you want to make, you can make it on one machine. Can you solve the problem on one machine, or you need a cluster? And our point of view, if you need a cluster, it doesn't matter, it's much matter what is the processing you want to run and how much time it takes, if it's answer your requirement. If you're running on a cluster, you're in a big data domain, while if you're in one node, it's not a big data domain. And mainly the reason is because of the algorithms, because algorithms on one machines are different than the algorithm that's written for distributed machines.
So if we're dealing with, let's say, a relational database with hundreds of millions of records, is this big data?
Yeah, we have a slightly different definition. So we have some argument whether if the data fits into a memory of a single machine, then it's not big data. I guess everyone will agree. But we claim that if the data can fit to a disk of one machine or a distributed storage file system, and you can still process it on one machine, then we get to the gray area whether this is big data or not. So actually, we do think it is big data. And regarding your specific question, 100 million rows in a table, it's a small data set in the kind of data set we're working on. Specifically, we have tools that can scale to billions and even hundreds of billions of rows on a single machine. But that's
So we took size, you mentioned size. What is the size for big data? You said billions. In terms of velocity, what do we define big data? Where are we entering the range of big data?
We need first to take into consideration that big data, it's not only for analytics. Big data can be for operationals as well. And the term big data is a new one, but it doesn't mean that people didn't do any big data like 20 years ago. There were systems, a cluster, distributed HPCs or databases. So big data has all sorts of usages. Some of them for machine learning, some of them operational for games like Farmville or any Facebook game with 200 million users that need to be work well for 200 million people, or having your Outlook. But there are big data solutions as well for analytics, for machine learning, where there is big data. It can be big or small, but there is different usage.
Okay, so now that we have some basic understanding what big data is, we'll move to the next topic. That is the technological challenges of dealing with the amounts of data, big data. So each one from your perspective, in your practice, what are the main challenges?
So, as we see it, there are two types of challenges. Usually we split it into two. So one of them is the data engineering, which is actually bringing the data, cleaning it, and making possible the analytics on top. So that's the main challenge we are facing. And the second challenge is how to do efficiently the analytics when the algorithms are, in many cases, complex and needs very heavy runs.
Yeah, to me, the main challenge is actually to separate between the infrastructure of big data and the applications of big data. So, like, I'm not perfectly sure. Like, we come from different, like, groups and industries. So when we're talking about big data, are we kind of concentrating on infrastructure, how to store, how to efficiently retrieve, how to search the big data, or we're talking about a specific application where we take, like, a terabyte of data, and out of the sudden we get something that people can use in their everyday life. So what I'm not perfectly sure about that. So we can talk about infrastructure, we can talk about application, but to me those are two separate issues. So we need to decide what we're talking about. Want to say something?
Yeah, I believe that these two topics are still connected, because at the end of the day, SAP as a service company is sensitive also to infrastructure costs. And we are constantly moving towards cloud-based scenarios and less often on-premise scenarios where we were less sensitive to infrastructure costs because it's on the customer. So for us, I believe it is as important to have high accuracy, maybe big data application, but also that this application will be efficient and fast, because users are used to the response times of Google search and of iPad. So in terms of UI and in terms of we need to return some answers to queries, we have to comply to these constraints defined by the consumer side of the industry, and it holds true for the enterprise users as well these days. So it is connected.
Whatever you're saying, essentially, like, if you're talking about real time problems, right? So the infrastructural part of this big data ecosystem is more important. Once you are talking about offline processing, then we care less about the infrastructure, and we care more about the accuracy and the quality. That's how I understood that, at least.
Yes, but accuracy and quality are obviously functions of how much iterations you do in your algorithms, and you can translate it in infrastructure costs again. So accuracy has its price. I mean, and if you deliver your service as a service, basically your customers doesn't care what it takes and how much infrastructure costs, and you have to somehow invent appropriate pricing model which will still allowed to maintain high accuracy, but not at all costs. So performance and efficiency of implementation of big data processing is very, very important for the enterprise, especially for cloud-based scenarios.
I want to answer your question regarding, and starting with the infrastructure. There is another revolution going with big data in infrastructure, is that the open source community is very active there. Unlike the databases that we have, mainly companies, mainly proprietary, the big data industry is driven by an open source mainly, a lot of solutions there. The maturity level is really, really different to what we used to in the proprietary solution. That's meaning that we must invest much more labor in those solutions in order to make them work. So this is, from one hand, a big challenge. From the other hand, open source is running much faster than proprietary. The amount of new algorithms and new capabilities it's amazing than what's happening in proprietary.
Assaf, you made a note now about other technological advances that are happening. You talk about open source. Earlier when we spoke, you also mentioned Lambda architecture and the Internet of Things. Maybe you want to comment on how these are related to big data?
Maybe the next buzz after the term big data is rising now is Internet of Things. And I'll say in 30 seconds what it is. It's a device somewhere connected to the internet and sending the sensor data, not only smartphone, but it can be temperature in a fab or camera or your Fitbit and any other device. And big data is part of the Internet of Things. The devices create data, they send it, a huge stream of data from a lot of various of devices. There is an engineering problem to collect the data, to store. Can we store the entire data? I don't think so. And we need to reduce the data during the way from the device into the cloud. But at the end, there a cloud that needs to do a big data store the data and run analytics on top of it. Just one thing you asked regarding Lambda architecture. Lambda architecture is the architecture of coming from the industry for Internet of Things, which means we have different processing methods. We have the stream of the data. We need to do some processing there. There is the batch, the offline, and there are other processing that's been done there. And there is the interactive layer. The user wants to interact with the data. These are three logical different processing. Can they be on the same platform and hardware and solution of big data? I don't think so right now, but that's the connection.
Yeah, so Internet of Things is sort of hype topic. Usually in Europe, we are, as a European company, German company originally, call it Industry 4.0. So in Europe, we use slightly different term and slightly less consumer-oriented. Basically, in the enterprise, we see Internet of Things as a consolidation of information, which was usually stored in enterprise silos on some sort of enterprise cloud. And then new types of applications suddenly become possible. So if we look at the, an example, automotive industry, then the trend today is that automotive vendors collect information from cars and store this information on their clouds. Like Volkswagen, they have their own cloud, General Motors, they have their own cloud, etc., right? Now they are interested to monetize this information. On the other side, there are fuel station operators and like fuel suppliers, etc., who are interested basically to attract customers. And SAP as an infrastructure vendor for these enterprises, is trying to build a marketplace and to broker this information from different cloud silos in one central place, so we can develop new types of applications and create new types of offerings and basically somehow correlate information coming out of vehicles with information coming out of, let's say, Shell gas stations or something like that, and create new markets and new applications for this. And we can connect it obviously with some municipality parkings, etc., and then create some targeted offerings for the customers, and everyone will be happy. So, from the enterprise perspective, from SAP perspective, Internet of Things is basically consolidation of information in the same place, and the processing of big data, and less of endpoint devices and collecting of all this information, embedded systems, etc.
Okay, so if you're moving from talking about the physical the infrastructure to applications, I consulted the members of the information systems group before this panel and asked them what would be the question that you would want to ask. And not surprisingly, most of the questions concerns the applications for big data. And some of the people asked about user modeling, the ability to create user model, update user model based on the velocity of the data, and also to use that information to personalize interactions, the implications for the design of information systems.
Those are two very useful areas, and we actually do a lot of work in these two regions. So basically one example of big data applications that are very popular these days are anything related to recommenders. So now things get way more personalized. Ads track you whenever you go. They know if you're on the iPhone and then on the computer that you're the same person. You know, they know what you search in Google, and later you see those ads track you. So a lot of effort on recommender systems, which is headed by big companies like Amazon and eBay and so on, that are very state-of-the-art, but others are trying to catch up. And a second area is a lot of user modeling, social networks, graphs between people. Also another area of many applications. And this is the kind of functionality that in academia we actually know how to solve. There are a lot of algorithms for that. In industry, the situation is way back. A lot of companies are still using rule-based systems, where they have their own smart analyst guy who comes and decides what are the rules to give persons the items they like or things like that. But now a lot of companies are interested in switching into more of a machine learning approach, black box approach, to understand from the data without the need of a human modeler for rules.
Machine learning solution were here before the big data term was, and people build the solution based on machine learning. Big data is just so costly to run, so you need to have a real ROI. And real ROI coming when you can prove you're improving something. When you give an analyst a tool and he's running reports and making his mind the assumption and then go and take an action, it's really hard to prove it. But when you build a machine learning solution that close the cycle and take out of the equation the person, it's really easy to quantify. And the combination of machine learning and big data is going very well together, because investing in big data is very costly, and machine learning have a good ROI to solve solution, and those two are going well together.
I agree that machine learning and big data do go well together. The only problem is that you actually have to kind of rebuild pretty much every machine learning solution to be able to run on big data. Trouble is that all the algorithms available so far, when people created those algorithms, they didn't think about that we will run it on terabytes of data. So the algorithms are very precise if you run it on a data set of 10,000 instances, but we have 10 billion. What do we do with that? So the algorithms are heavy, and it turns out that you cannot just take a heavy algorithm and try to parallelize it. First of all, it's not easy to parallelize it in most cases. And if it is easy, then it's the algorithm is not really good. And the second is that even if you parallelize a heavy algorithm, it's still not, so you lose accuracy in many cases just because of the artifacts of the parallelization. So you end up with a solution that is either very, very simplistic and it does run on big data, or it's a solution that is very complex and you have no chance to apply it to big data. So this is the trouble that we are trying to solve, and we are trying to come up with solutions. So, you know, good algorithms, well parallelized, that we can apply to big data.
Another kind of application that people in the audience were interested in was the combination of bottom-up processes working with big data and top-down. So assume that you have some kind of formal representation of a domain. You have a user in the medical domain, and you have big data bottom-up. How do you combine the two? We're doing justice to the questions. Lina, more?
So one great example to a similar approach is what we call deep learning, which is another buzzword, which basically builds a model of image, how the images are constructed in order to be able to classify images. And this is also one of the areas where maybe 5 years ago it was almost non-usable because the algorithm was too heavy, as we discussed. But only in the last 2 or 3 years, actually, with the inclusion of better hardware and GPUs, we'll start to see way better implementations to solve this kind of methods. And now we got, I think that this year we got to the stage that the computer is slightly better than a human in recognizing objects and images. So that's kind of a breakthrough. I think it's both of them are like 4% point something, but computer is slightly better. So that's either encouraging or frightening. I must tell another story which is related. One of the weirdest applications that I've encountered, because we have a deep learning toolkit, so we work with customers. And it also relates to the Internet of Things we discussed. So one of the strangest applications is actually cameras inside of trash bins. So believe it or not, there is a company who is putting cameras inside of trash bins. The cameras are connected to 2G wireless, and every half an hour sends the image into the main server. And initially, the way they work, they actually took a lot of Indians that sit and get, I don't know, 1/10 of a cent for each image. They decide if the trash bin is full or not. And once the trash bin is full enough, they send the truck to remove it. And now we're actually using deep learning to solve it way better than human can.
It's a good example, but not in every case you can use a mechanical Turk approach, right? So there are some cases where you need to deal with retinopathy or mammography images analysis or something like that, and then you need highly trained specialists. And usually these specialists are not clonable or scalable or whatsoever. So whenever we will get to the point where the accuracy of analysis of medical imaging will be high, it will help probably to democratize the access to this high-quality medicine also in developing parts of the world, etc. So from this perspective, SAP is looking very closely at the domain, and currently we are building our own personalized medicine function, which try to exploit all these capabilities. So industry is going after that. From some perspective, it kind of a disruption because some of the jobs probably will be gone, but from the other perspective, it will definitely make the world better. So,
you talk about looking at from bottom of a top, and I want to propose another option to see that. We said machine learning and big data, they should go going well together, but it's still the start. What I mean, it's machine learning. Basically, people with machine learning expertise are today almost cannot consume big data platform, and the ones that develop on top of big data platform are mostly engineers and unicorns that can do both of them are really rare. So today, in order to solve a solution of big data and machine learning, you need those both expertise and teams. Big data platforms are not consumable by data scientists, and this is a big problem. So during development, for example, and exploration, everybody work in his separate environment, and only for production there is made an effort to make the mix itself.
How do you see the solution to that?
I think we start to see companies that going in two ways. One is saying we want to eliminate the data scientists. We want to automate the process of building a model and processing the data. This is or what's called finding the holy grail. Maybe it's feasible for some problems that are more we're familiar with. And the other direction is that slowly there are, we see people starting to move solutions like for one machine like R or Python and try to build the same algorithm as you mentioned one by one on a distributed system. I hope that in 2 years when we have a problem in data in the big data, we don't need to offload it to the computer of the data scientist, and it will be able to work on the platform itself. But currently, it's not the situation.
Yeah, I would probably add something from the academic perspective that, there are two different fields, AI, artificial intelligence, and systems. And those two different fields in computer science don't really talk together that well so far. Well, we know stories, right? So the trend is it really looks like AI folks are becoming systems people. Just because to build a very complex and beautiful AI model is not enough nowadays. You need to know how to apply it to the real data, and the real data is no longer 10,000 data instances. And we do lack some skills. I am coming from the AI field, right? So we do lack the skills of systems, and we don't really know how to bring those beautiful algorithms to the amounts of data that out of the sudden we got exposed to. Even 5 years ago, 10,000 data instances was kind of fine to write a paper. But 5 years ago in the industry, no one cared about 10,000 data instances. Nowadays, it really looks like that. Even in academia, we don't really care about data sets of that size. We really want to work with millions and billions. And here's the gap that we need to kind of complete our second PhD in systems to close this gap and to be able to process big amounts of data with the models that we have been developing for the last 20, 30 years.
So since the questions about applications came from the audience, or part of the audience, maybe before we move to the next topic that we have, we'll pause for a second, see if the audience has any questions about applications. Mo, please.
Yeah, my question, I come from the medical domain, and we have a large body of knowledge that came from studies, controlled studies with patients, in which you propose you have to separate the homogeneous population into two groups, and you have two arms, you study two interventions, and you see which works. So this is how knowledge was traditionally generated. Now comes a patient who doesn't match exactly the population in the study. And on the other hand, you have a lot of data collected on patients. is there any statistical methods that will help me to integrate this knowledge that I already have from the controlled studies with what you mine in uncontrolled environments?
Yeah, so actually that's a topic which often comes up, and we actually have some tools for that in the domain of transfer learning. So one of the nice work that I've seen in this domain, and I'll be happy to share anyone who's interested, in the area of deep learning, for example, so there are data sets of, there is a Kaggle competition which is called cats versus dogs. And the idea there is that you have a very big repository of dog images, and then the test set is actually cats images. And the question is, can you learn from dogs in order to improve the prediction in cats? And it actually, we can utilize information from a different domain, from slightly different population, and still improve the model. So yes.
Another way of working, I think, we have a project that we do with in my team with Michael J. Fox Foundation in the Parkinson domain, where the goal is to collect 24/7 data of patients in their home environment in order to create a big repository that help a researcher to hopefully have a breakthrough. So we collect wearable data, GPS. We do the entire work in order of building our models in controlled environment. We have controlled environment, we bring patients. It's very costly, but at the end we use off-the-shelf devices that cost $99, and everyone can buy them. And we try to combine it with a solution that, in a while, in home and not in controlled environment, gets feedbacks from the patients, and hopefully to improve the system like that.
As I interpret Moore's question is more about like combining small data that you gain from a controlled experiment with the big data that is somewhere out there. So it is a big trouble. Of course, it's very difficult, not only from the perspective that you need to somehow have a match between those two data sets, which is mostly done manually, I would say. But since one of the data sets is small, it's kind of feasible, I think. The trouble is that those two populations, your controlled experiment is not being sampled uniformly at random from this huge data set that you have. So you have some type of skewness. And this skewness cannot be resolved very easily. My take on that is that you basically, I would love to see all these fields of medical fields and many other fields when the controlled experiment is pretty much the only mechanism to move out of that world of small data, just to do your controlled experiment on millions of people. I don't know how exactly you do that. In some cases, it's not possible. In some cases, it might be. And we have many, examples that come from Google that they kind of measure what people talk about, like, flu outbreak and stuff like that. So it is possible in some domains. And I really hope that in some time, probably it's not going to happen within 5 years, but we will just stop testing this drug on these 10 people, because you can be a very good statistician and prove, theoretically, that it actually is the good sample, and you are bringing an absolutely perfect solution based on these 10 people. But well, I'm not a trained statistician. I have my doubts on that. And I hope that the systems are out there. So not in the medical domain, but say, for example, in the domain of the internet, we have this A/B test, right? It's a very similar test, but it is done on millions, if not billions, of people in some domains. For example, an anecdote is coming from Yahoo. When they rebuild their homepage, they heavily use this A/B test mechanism. They just try to see what works better on their home page. And since many people access Yahoo from yahoo.com, everything on that page brings billions of dollars. So like it's very important to do it in a way such that it maximizes the gain for the company at the end of the day. And they did do that, and they did improve their revenues through that. So it is possible. The technology is it exists. The only problem is it's more like the regulations. For example, I guess this control study goes through all this regulation and has to be improved. Now, if you do a very similar thing on 10 million users, I don't know how it's going to work. That's one thing. And another thing is that obviously in some cases it cannot work, right? You cannot apply this drug to 10 million people. So like you will have only partial solutions to some of the problems that are available.
I want to now move to a slightly different topic, and some of you alluded to the notion of practice, and we're in academia interested in education. And I mean, if you open the recruiting pages in the newspapers, everybody's looking for data scientists, one of the hardest jobs nowadays. I mean, we pay handsomely for data scientists, and we're here at the academic institutions are thinking, how can we prepare the graduates to compete in this job market? And there's actually some discussions here at the University of Haifa between the computer science department, the statistics department, and information systems on setting up a data science program. So from your perspectives, what do we need to prepare the graduates for?
This is a tough question, and especially I'm from the Hebrew University, so there, if you do anything practical, you are doomed, more or less. One of the new professors there, they consulted me. They want to start teaching a data science course about parallel programming, and they've decided to teach MPI, which is about 25 years back than what they need to teach, but that's the decision. So I can only say bad things about the organization I came from. I don't know what's going on here. I know, for example, in Ben Gurion, there is very, very good emphasis on the applied side. That's what we see. So we actually hire people from there. They have good training for us. So I think basically you need to take a step back from just theory of machine learning, which is fine for writing papers. But in the applied side, there is a lot of emphasis of how to make things that work quickly without a cost of 10 years of research. So sometimes solutions are preferred to be simple. In many cases, companies want to have 80% accuracy, and it's not interesting to get to 90% accuracy if it's 10 times more work. So there is always a trade-off between the accuracy and the investment you need to make.
From skill set perspective, it's at least three main different skill sets. Danny mentioned machine learning. Secondly is computer science or software development skills. And if you put big data into the software development, so there you as well must have some kind of infrastructure. You cannot run big data on your laptop anymore. You can download the VM, but it's not really working. And you as a university, you must invest in a lab of big data, which is costly. We built one in Ben Gurion. It costs over $1,000. And the third that people sometimes miss is business understanding. Still, we're doing information system. We need to solve business problem. We need to implement it in the organization. We have the same problem of BI. That we just climbed the curve of the BI maturity. So we need to have solution that has return of investment, and the organization is really needed. And if there is people that use it, so they must use it. And there was always a question whether we want to build a unicorn that do all of them. It's one person, and there are companies that go in that direction that will do everything. He'll get the data, he'll transform it, he'll find the features, he'll find the models, he'll implement it in production and understand the business. Or we want to build teams that we have their machine learning expert, we have the software development, we have the people with business acumen. They all must have some basic level in machine learning. They all some have basic level in software development, but each stage is led by the person that's relevant to the stage, and the team is responsible from the start to the end of the project.
Both you and Danny don't mention databases. Right? We will teach relational databases. I assume computer science they also teach relational databases. We need to start teaching Hadoop and other.
So Hadoop is a database. It's just not relational.
Yes.
You need to decide what direction you want to go. First, you want to focus in the analytics side or the operational side. You're going to want to go, and then by these basic needs, there are different application solutions that's built on top of them.
Yeah, actually, pretty much agree with Assaf. It is really hard to combine analytical skills with probably computer architecture, understanding skills, or something like that. So it's a different mindset. Some people are interested and comfortable to work with numbers and data, and they don't care basically how this data is stored inside of the computer system, how it's being processed, how many cores, what is NUMA effect, and what is cluster or whatever. They just want to work with numbers, and whenever it comes to productive scenarios, then there are other people who know how to scale this stuff. So I believe it is hard to combine all these skills in one person, but obviously for the university, it will be worthwhile to combine studies of relational databases, which are still there, which are still important part of enterprise applications, and SAP is building that, Microsoft is building that, I mean, Oracle is building that. Even on top of Hadoop, you have SQL interface, so SQL will be here for a long time. But on the other hand, there are like new tools emerging, like Coffee, like Tiano, like Torch, like GraphLab, like Spark. So all these tools and ability to use these tools is very important. I mean, usually what we see when we look for data scientists, at best they know how to instrument MATLAB and R, which is nice, but not enough, because R is not very scalable and MATLAB is not very scalable as well. Even though these two tools are starting to support some algorithms, GPUs, etc., I mean, it's not enough and it is not scalable. It's good for modeling, it's good for playing with data and validating different approaches. Maybe this is nice, but when we need to deploy a real application which will consolidate information from, I don't know, different seaports and container movement or some car movement on Russian railways, one of the customers, an example, then I mean, it has to be fast and it has to be able to process big data, and R is not a tool for that.
I agree that definitely using R and MATLAB is definitely not enough for big data. So to me, first of all, I'm making some type of differentiation between data science and big data, meaning that a data scientist might process small data and find interesting insights in the small data, and that's perfectly fine. So if a data scientist has an access to big data, that's even better, right? So it might be more interesting insights from the big data itself. So the question, well, I'm coming from academia, right? So like to me, it's important whether we are going to teach data science or big data, or both in the same class or in two separate classes. This is not extremely obvious right now. So I'm actually at the Faculty of Management. So we have two programs. One is MBA that is not really related to big data, and another one is MA in Information and Knowledge Management. And we are running, for the last 2 years, we've been running a pilot of teaching data science to essentially business people, those who come to do their masters and PhDs in the Faculty of Management. And it's a completely different approach from what I guess is what anyone is talking about, which is take the engineers and teach them how to solve big data problems. We are taking a different approach, which is take people who come from product management, who come from business development, who come from the world of business, and teach them how important the data is in their everyday work, how they say, experience. So it's the same problem from a completely different angle. So I'm actually teaching them how to write Python, how to analyze data with Python. It in some cases it doesn't work that well because some people are saying like, you know, I can't do that. But it turns out that like 90% of those folks actually can manage to write Python at the end of the day. And what is really important is that they really get the idea that you cannot do business without doing data. And this is essentially probably even more important nowadays than to take all the engineers and show it, give them all the tools to process big data, because like we are going to be there this way or that way. When you look at the businessman, this is not clear. It's not obvious to them that data is going to be the next business. So we're trying to do that, and I guess we're pretty successful with that. So like to me, the skills that we need to acquire is basically the main skill of looking at the data, understanding the data, and making insights from the data that would help your business. At the end of the day, the engineers, we are all engineers here, it's a minority. The world is not built of engineers, the world is built of everyone else. And if those folks cannot understand that without data we cannot solve real business problems nowadays, that the world is not going to be going in the right direction. So this is essentially what we are focusing on at the Faculty of Management.
Okay, so as we're getting close to the end of this session, maybe there's an opportunity to ask the audience to participate initially on the topic of educating for big data. And I'm guessing that we will have some interest. Shooting? No?
One aspect we didn't address is the visualization of the analysis of big data. Cognitive aspects of how to understand your analysis. Do you have these issues?
It's a very good topic, and I had it. I wanted to talk about that, but was distracted by someone trying to reach me on the phone. Yes, yeah. As a part of our job, actually, we do some market analysis of the domain of machine learning for SAP globally, right? Because many enterprises are trying to enter this domain at the moment, and we see a lot of offerings as infrastructure, building blocks, complete infrastructures, maybe algorithms, etc. But when it comes to big data visualization, actually there are not that much offerings out there, and it's really amazing. I mean, I'm aware of maybe like 2 or 3 companies as opposed of tens or maybe hundreds of companies in the domain of data processing and data visualization. So, I mean, one of these, I was introduced by graphistry, right? So these guys are trying to visualize really big graphs, and there are some approaches actually trying to leverage maybe even some things from art, like cubism or something like that, to represent big data. So yeah, so this domain is not crowded at the moment. Obviously, there is a need, because when it comes to big data, visualization is neglected while we are busy with the infrastructure. But at the end of the day, we have to visualize it somehow, and even tools like Tableau or SAP Lumira are not enough at the moment. So yeah, this is definitely area to explore, and it is not saturated at the moment.
I think we need to take into consideration that big data from database take us like 30 years back. Like, our processes are not running, the environment is not stable, there is almost no security there. We need to migrate the beautiful set of 4,000 R packages into the big data platforms. We have so many problems, and so I guess the industry is not focusing right now in visualization.
Also, the issue with visualization, it's way more difficult to visualize. So we, for example, worked a lot on graphs, and once you have a graph with more than 1,000 edges, you simply cannot draw it. It becomes a mess. So think about a graph with 200 billion edges. It's very hard to visualize, and actually you need to do a lot of pre-processing and maybe hierarchical algorithms and things like that in order to do a lot of pre-processing, and then you have a simple visualization. So that's really an issue.
I'm curious, especially in the industry, because when you think of machine learning in the industry, what do you mean by machine learning?
Automation of analysis of the data, which is very simple, and the disruption will come from this angle, and it is not possible to maintain huge divisions of people who create all these rules and regular expressions and change these regular expressions on a daily basis in order to adapt to constantly changing maybe unstructured data or documents, etc. So at the end of the day, industry is looking for automated solutions, industry is looking for classifiers, industry is looking closely at deep learning techniques, because otherwise it will be not scalable.
We actually have a conference coming up on May 11, which is the first Israeli Big Data Analytics Conference, and 30 companies are going to present what they are doing, and we really selected the state-of-the-art. So we had a high selection process, and we have a significant discount for students. It's only 50 NIS, so everyone is welcome to attend.
And we have 7 visitors from abroad coming, including Google, O'Reilly, Datto, Intel, and Bloomberg, and NASA, and much more.
So to your question, deep learning today is definitely a hype, but industry is looking very close at this and checking whether these solutions will be highly accurate and efficient in order to implement. As soon as we will feel comfortable, these solutions will be immediately embedded and implemented.
So first of all, I want to thank the distinguished speakers, Israel's top experts on big data, for coming here from all the way from Tel Aviv or the center. Jerusalem even, wow, okay. Thank the Information Systems Group for organizing this session, and the audience, and the Cule Institute for organizing the international event. Thank you all.